Welcome to problem solving session for the course Linear Algebra. Today we will discuss problems related to syllabus from week 2, that is problems related to examples of subspaces and sums of subspaces. And I'm Siddhi Balu Ambore from IIT Gandhinagar. And let us start with the first question for today's problem solving session. So, for example, for real numbers a and b from R, the straight line LAB is equal to, so we are looking at the straight lines in R2 satisfying this equation ax plus by is equal to 0, and they are saying that these are subspaces of the R vector space.
Ma'am, is
Yes.
this recording available on the site?
Yes, it is available on the YouTube. And for to access the link, there is on the portal there is one section at the bottom, problem solving session. If you click on that section, there is one Excel sheet where this recording will be available. And for my course, the notes will also be available. So if you are writing, you do not need it because this will be shared with you. And you can access the video and this lectures, these notes uh, after an hour of this, after an hour, this session ends. Yeah,
Okay, ma'am.
yeah, sure.
There are two tutors for this course.
Yes,
So,
there are two tutors for this course who are conducting live live problem solving sessions. Yes.
okay, so the problem solving you both are conducting are independent, or you are teaching what she's not teaching.
No, it is completely independent. I am just conducting what I feel is necessary, and she is doing. Maybe we are covering topics which overlap, or we might be covering topics which are not overlapping. It is just two sessions because there is a huge strength for this course. And if someone misses the session on Monday, they can attend the session on Tuesday, and that's it. Apart from that, I do not feel there is any difference. But yeah, there could be overlapping, or someone might be covering something extra than the other person, depending on the pace. Yes. But
Okay.
mostly the problems will be from the tutorial sheet which is shared with you in the assignment. Uh, I hardly doubt if the other person will be solving some problems other than that. Yes.
Yes, ma'am, it same.
Okay. So R vector space.
Hello, ma'am. One more question.
Yes, sir.
Hello.
Yes, sir.
Yes. Is our examinations will be like MCQ or writing written examinations?
Okay. So that I do not know, to be honest, because I will not be dealing with that. The assignment grading, and exam and grading of the exam. So I really do not know. But if you have this question, please raise it in the discussion forum, and the respective team will definitely reply to that.
Okay. Thank you.
Yeah, sure. Okay. So the question is, the for real number a and b in A and B, the straight line defined by denoted by LAB, which is collection of all the points x, y in R2 satisfying the equation ax plus by is equal to 0, are subspaces of R2. And but for C belong to R such that C non-zero, the straight lines LABC xy in R2 such that ax plus by is equal to C. This is subset of R2. Are not subspaces of the R vector space R2. So last time we saw what vector space is. So let us recall the definition of subspace, what subspace means. So let V be the vector space over the field K, and a subset U of V is a subspace of V if with same addition and scalar multiplication from V, U is a K vector space. So when I say K vector space, it means vector space over K. Okay, so that is the definition. And what, so the K vector space structure on V on U is induced by the given K vector space structure of V. So we know that for solving, when we say a particular set is vector space over K, there are few properties apart from the addition and scalar multiplication being closed operation. So, but when we say something is a subspace of the given vector space V, we look at the same addition and scalar multiplication, and it itself should satisfy all the vector space properties. Okay, and they say that K vector space structure on U is induced by given K vector space structure of V. It means the addition and scalar multiplication behaving exactly same as they are behaving in V. Okay, so this is really important, that with the same addition and scalar multiplication from V. Okay, then only we can say that it is subspace of given vector space V. Okay, so we have to check now this, that this LAB, so now what we have to check, that this LAB, this set is a vector space. We have to check this. Is a vector subspace of R2, R vector subspace of R2. And so for that, we have this subspace criteria. If you have gone through the notes, and it is that let U be contained in V, then U is a subspace of V if and only if first that 0 belongs to this U, second that if X and Y in U belong to U, then X plus Y must also belong to U. And third is if A belongs to K and X belongs to U, then AX belongs to U. So in general, to check if particular set is a, it will be written. Priyansh, could you please explain what you wanted to say? It will be written. Okay. So what I was saying that so the instead of checking all the criterias whether U satisfy all the vector space criterias or not, just to check whether particular set is a subspace or not, we only need to check these three properties, whether 0 belongs to the set and whether the addition and scalar multiplication here induced from the given original vector space are closed or not in that set. That is enough for us to declare that something is a subspace or not. So we will be doing that. So first we need to check whether 0, 0 belongs to the set or not. So 0 in R2 means the is actually this point 0, 0 in R2. And we have to check that whether this 0, 0 belongs to U or not. So what we need to check that this U belongs to LAB. So what we need to check is whether AX plus BY is equal to 0 or not for XY is equal to 0, 0. That is A0 plus B0, B into 0, which is 0 is satisfied. Therefore, this actually belongs to LAB. So we just check that 0 belongs to that set. And if I take these 2 points, x1, y1 and x2, y2 in R2 in this LAB, then what does this imply? This AX1 plus BY1 is equal to 0 and AX2 plus BY2 is equal to 0. Okay, so now we have to check whether x1, y1 plus x2, y2 belongs to LAB or not. That is, we need to check whether this x1 plus x2, comma y1 plus y2, whether this belongs to this line AB, line LAB or not. So what we need to check, so what we need to prove that this LX1, x2 plus B, that is BY1 plus y2 is 0 or not. This is what we need to check. So let us start with left hand side, that AX1 plus x2 plus BY1 plus y2. This will give me this plus BY1 plus BY2. And since now this every calculation is happening in R, which we know is a vector space and addition is commutative and so on, we get that AX1 plus BY1, we can just shuffle this two terms and we get this is 0 since x1 comma y1 belongs to LAB, and this is 0 because x2 comma y2 belongs to LAB. So this is indeed 0 plus 0, and this is what we wanted to prove. So therefore this x1 plus x2, y1 plus y2 belongs to this subspace. Not subspace, yes, to in this set. Okay, and the third property we need to check is for any given A in C in R. Let me not use C. Let us take D in R. We have an x1 comma y1 in R2 in LAB. We need to check that this D x1 y1 is 0 or not. That is this, sorry, belongs to my line A LAB. That is whether dx1 dx2 belongs to LAB. So this, when I write that d x1 comma y1 is equal to d x2 comma y2, sorry, x1 y1, this I can write because we know the scalar multiplication. This is scalar multiplication from R2 as R vector space. And I need to check this whether under this scalar multiplication I get the way this scalar multiplication defined in R2, whether it is satisfied and it is closed in this line LAB or not. So what I need to check is that is this D A x1 plus, not like A D x1 plus A B D. Okay, I'm using x1 y1, so let me stick to that. Is 0 or not? So I need to check this. Okay, so if I start with left hand side, it is just a dx1 plus b dy1. And since we are in real numbers, this is what? And this is 0 because x1, y1. Ma'am, what is the composition of it? Okay, just a sec. Let me just finish this and then I will x1, y1 in LAB. And this is now 0, and this is what we wanted to check. So therefore, this d x1 y1 belongs to LAB, and so it satisfies all the three criterias, that this L0 belongs to the line LAB, then the addition of two vectors belongs to the line, and scalar multiplication of two vectors also belong to the line. So therefore it satisfies all the three criterias given in, let me just use another color, this subspace criteria, and that's why we can conclude that therefore this LAB is subspace of R, subspace of R2 as R vector space. R vector space because, okay, yeah, so the structure which we are talking about is, so we started with to answer the question asked in the chat. So we started with the subspace of R, not subspace. So we wanted to check whether this given set is whether it is vector subspace of R2 or not. And that's what we are trying to see. So when we say something is a vector subspace of particular uh, uh, vector space, what we need to check is that the subset which we are considering must be a vector space in itself, satisfying the cell under the same addition and same scalar multiplication. So when we are doing this addition here and scalar multiplication, wait, where is, yeah, when I'm doing this, I'm following this addition, sorry, not this one. I'm following this addition from the structure of R2 as R vector space. Okay, so there are many ways we can define a vector structure, vector space structure, or addition on R2 as a R vector space. Okay, so but when I'm looking at this LAB as a R2, as a subspace of R2 or subset of R2, and I have to check that whether it is a subspace of R2 under the same addition and scalar multiplication defined in R2. So how we add and subtract in R2? So R2 we add and subtract this way, right? This is standard structure on R2. And scalar multiplication we define like this: alpha x1, alpha y1, where this alpha belongs to R. So when I'm checking that LAB is a subspace under this scalar multiplication and this addition, I need to check these properties. For example, I can add them in very different way. For example, some other vector space structure on R2. I can take this, maybe x1 plus y1 plus x2 y2, I can add them like this, x1 plus x2 and 0. This is my addition. I can define this addition, and you can check that this will still form a vector space structure on R2. And again, I will define this alpha x1 y1 to be alpha x1 comma 0. This. I'm defining the addition this way, and this is still a vector space. You can check, okay? Under this addition, so if I do this addition in some different color and this scalar multiplication in some, let me just change. So this is also addition and scalar multiplication defined like this, and this will still give me a vector space structure on R2. But this R2, maybe I can do it R2 bar. This is very bad notation, but this is again a vector space over R. You can check that. But and when we say that particular set is a subspace of this vector space, then I have to look at the addition and scalar multiplication in this context. Then I can't do addition and scalar multiplication like this. Okay, I hope you understand what I'm trying to say. So when I'm looking at particular set is a subspace of a given vector space, the addition and scalar multiplication should be followed and induced from the big superset or the bigger set which we are looking at. So that's what I said. This. So when you ask this composition of two elements, I hope that's what you wanted to ask. So scalar multiplication and addition, when we check for the subspace, we have to look at how the addition and scalar multiplication is defined in the original vector space to start with. I hope that was the question. Okay, I hope that is clear. But yeah, so now this was the first, and now second part of the question they are asking is that to check whether this LABC, that is this xy in R2, such that ax plus by is equal to c, and this c is non-zero, by the way. So let me write this properly. ABC in R2, sorry, in R, and c is non-zero. This is not a vector subspace of R2. So can someone tell me why this is not a vector subspace of R2?
It will not be closed.
Yes, it is not close. Because yeah, when we add 2 points, it will give me addition to be 2c1, but I won't see. So 2c. So what? I think it was Vinayak maybe. I don't. So as someone pointed out, it is thus. Let me take this. Suppose these 2 points, they belong to my LABC, and when I add those and I check for this, then this x1 x2 plus by1 y2, if I simplify, this will be ax1 plus this ax1 plus by1 plus ax2 plus by2, and this will be 2c, and not, because this is c and this is c. So this is 2c, but I wanted this to be equal to, actually, but for this to belong to LABC, I wanted this to be equal to C, right? So the condition for the addition of two vectors to land in LABC is not satisfied. And even if you do not want to go to this, you can simply check whether 0, 0 belongs to this LABC or not, which is the basic for something. I mean, we need to have 0 in the vector space. And so if we check whether this 0, 0 belongs to the set or not, so I want what? A0 plus B0 to be equal to C. So this is 0 is equal to C, but we are given that C is non-zero. So therefore, 0, 0 does not belong to this LABC. So the criteria which are given, the very first criteria, that whether the 0 of the vector space must also belong to the subspace, is not satisfied. And as pointed, it is also not closed under addition, and you can also check that it will also be not closed under scalar multiplication, because if I take some non-zero scalar and multiply it, on the left hand side you will get some alpha times C, but on the right hand side you will still be having C. So yeah, what I'm saying is, if we take up alpha non-zero and alpha in R, then not even non-zero, if I take any alpha in R, then if I want to check whether this alpha x1, alpha y2, whether this belongs to R2 or not, sorry, not R2, LABC, let me write properly, alpha belongs to R. And we have to check whether this belongs to R or not. Then this A alpha x1 plus B alpha y2 will be alpha into A x1 plus B y2. And this is alpha times C. And if I take alpha not equal to 1, this will not be equal to C, which we wanted for something to land in the set LABC or lie on this line LABC. So yes, so this therefore LABC, when C is non-zero, does not form a vector subspace of R2, because 0 does not belong there and all the closure property does not satisfy. But when this C is non-zero, then it happens, because when we look at, so this is uh, R2, and if I take any line which is not passing through origin, it does not, it does not contain the 0, 0 point, right? So it does not contain 0. So it anyway does not satisfy the basic condition for the first criteria for something to be subspace. But if I take some other line which is passing through 0, 0, then definitely 0, 0 belongs to that line. And if I take any 2 points and add them, they will still land on the same line, maybe somewhere here. Okay, so for example, yeah. So that's why once it passes through 0, it satisfies all the properties for something to be subspace. But if it does not pass through 0, we just saw that it does not satisfy the properties for subspace of R2. Is this clear?
Yes, ma'am.
Yeah. If you have any doubts, please stop and ask. And if you can't then unmute, then please ask the question in chat. The next question is similar to what we are discussing. So now we again have to check the subspace U is equal to, not subspace, subset U is equal to x comma y in R2 such that, so let me just forward, therefore LABC is not a subspace. So the next question is that U is, again we are talking about subset of R2, 4xy minus 4y square, and this U prime or U dash, whatever you want to call it, is again a subset of R2 with this property, 4x minus 4y square is equal to 0. R, we have to check whether these are subspaces of R vector space R2 or not. And again, the scalar multiplication and addition is do as we do in standard setup. Okay, so first one, let us check for this, and we will again be using the subspace criteria. So let us simplify this before we move ahead. So x square is equal to 4xy minus 4y square. So if I simplify this, this is x square minus 4xy minus 4y square, this to be equal to 0. So this is what? This is my x minus 2y whole square. But again, we are in real number. So if square of a particular number is 0, then that number needs to be 0. So this x minus 2y must be 0. So this give me that x must be equal to 2y. So this set U actually boils down to this set xy in R2 such that, yeah, such that x is equal to 2y. Is this clear? We are just simplifying the set, the given condition on the set, so that it will be easier for us to check whether the given set is given subset is a subspace or not. Okay, now we have to check again those three properties, whether 0, 0 belongs to this set U or not, whether check, let me write, check 0, 0 belongs to U or not. And what I need to check is whether x is equal to 2y, that is whether, so what I want is 0 is equal to 2y or not, but yes, 2 into 0 or not, but it is satisfied. This equation, so x is equal to 2y is satisfied by xy is equal to 0, 0. Therefore, this belongs to my set U. And now second is again, suppose I take this xy1 and x2, y2 in U. Now I have to check that whether this x1 plus x2, y1 plus y2 belong to this set U or not. So what I need to check is, that is to check whether this x1 plus x2 is equal to 2y1 plus y2 or not. Okay, but if I start with LHS, then it is x1 plus x2. But since x1 comma y1 belongs and x2 comma y2 belongs to U, this implies that x1 is 2y1 and x2 is 2y2. So this is what, 2y1 plus 2y2, just substituting what I have. And then this is what I get, that this is 2y1. And this is what I wanted to check whether, okay, so this is this condition that I need x is equal to 2y is satisfied by the addition of two vectors. So therefore, the second condition is satisfied. Therefore, this x1 plus x2, y1 plus y2, this belong to my set U. And now the third condition is, let this C belongs to R and my x1, y1 belongs to U. I have to check again this Cx1, Cy1 belongs to U or not. So I just need to check whether Cx1, that is whether Cx1 is equal to 2Cy1 or not. This is the question. So if I start with 2x1 and this implies that x1 is equal to 2y1. So this is, sorry, yeah, this is Cx1, but this x1 is 2y1. So I can just shuffle the multiplication, and this is what I wanted to check. So these are very basic check uh, basic things which we are checking here. But yeah, the main crux for this question was to simplify this equation, I mean, this difficult looking equation to this form. And you could directly, and once we have this, so this, when I write, this goes to, I mean, if you check, since I said, let me just write here. This u is what? X plus y in R2 such that x is equal to 2y. So if I rewrite this, this is exactly x minus 2y is equal to 0. And if I see what I proved in my earlier question, it is that for all this LAB is a subspace of R2 for all AB in R2, right? So if I take my A to be 1 and B to be minus 2, then what is L 1 comma minus 2? It is all those xy in R2 such that x minus 2y, right? So it will be x plus minus 2y is equal to 0, but that is nothing but x minus 2y is equal to 0. And this is exactly what my u is, right? This is exactly what my u is. So I do not even need to solve, I mean, I do not even had to check all these properties, whether 0 belongs, whether it is closed under addition or not, and the scalar multiplication part. I could just directly see that the u set which we have here is actually our L1 minus 2, which we already proved in general sense that it is a line passing through origin and the point, what point belong here? Minus 2, 1? No, 2, 1. Passing through 0 and point 2, 1. Yes. So, so this was pretty easy to verify whether the given subset is a vector space or not. Now let us see the next set which they have given. Sorry. Oh, yeah. Now to check the second part, that is u dash is equal to, this is bit different than what we did for, this is x square minus 4y square is equal to 0. So this is x comma y in R2 such that I'm just simplifying to, this is what, this is x square minus 2y square is equal to 0. So this is x minus 2y and x plus 2y is equal to 0. So this is what this set is. And if you further want to check, this just imply either x is equal to 2y or x is equal to minus 2y. I'm just simplifying this because we might need this to prove the subspace structure on this u dash. So first, whether 0, 0 belongs to this u dash or not. So clearly, 0 square minus 2 into 0, oh, sorry, 4, 0 square is equal to 0. So therefore, definitely 0, 0 belongs to this u dash. I'm not writing all the details because we already have gone through enough of examples. So now let us check this whether it is closed under addition or not. So let x1, y1 and x2, y2 belongs to this u dash. Now we have to check whether this x1 plus x2 and y1 plus y2, whether this belongs to u dash or not. So let us start with LHS and let us see whether we get what we need or not. So once I have this, this means x1 is equal to 2y1 or x1 is equal to minus 2y1 and x2 is equal to 2y2 or x2 is equal to minus 2y2. And what I need to check is whether this, so if I try to simplify this, so I need to check this x1 plus x2 square, right, minus 4y1 plus y2 square, whether this is 0 or not. So this will not be as easy as it was in the case of you. So let us start and check. So consider this x1 plus x2 square minus 4y1 plus y2 square. So this will be what? x1 square plus 2x1 x2 plus x2 square plus minus 4y1 square plus 2y1 y2 plus y2 square. Okay, and this will give me x1 square. So at the same time, I'm clubbing what is there with us. x2 square minus 4y2 square. This we have plus this term 2x1 x2 minus 8y1 y2. So we already know that this is 0 and this is 0 since, let me use another color. This is 0 and this is 0 since x1 y1 and x2 y2 belongs to my set u dash. Okay, so now we only need to check whether this 2x1 2x1 x2 minus 8y1 y2. So we have to check whether this 2x1 x2 minus 8y1 y2, whether this is 0 or not. And anyone has any suggestion or idea like how to prove this or how to check this? So note that we have these four conditions. Okay. So we have this with us that x1 is equal to 2y1 or x1 is equal to minus 2y1, or I have this and x2 is equal to 2y2 or x2 is equal to 2 minus 2y2, right? This is what we have. So there are four possibilities, and if I substitute each, and if I take two at a time, and if so, there are four possibilities. This plus this. I mean, if I point this 1, 2, 3, 4, so it is either 1, 3, 1, 4, 2, 3, 2, 4. So if I check, if I can prove that in all the four possibilities, I'm always getting 0, then I can conclude that what I'm having. So then I can conclude that this addition of two vectors actually belong to my set U dash. Okay, so if x1 is equal to 2y1 and x2 is equal to 2y2, that in that case, this 2x1, this will be what? 2 into 2y1. Am I correct? Yes, plus x2. And if I substitute this multiplication is correct, right? 4, 2. 2 into x1, and for x2 if I substitute 2y1, and for y1 if I substitute x1 by 2 and this is y2, then this is 2 x1, y1 minus, sorry, this is x2, right? Can someone suggest something? Because what problem we are facing here is that 2x1, if I substitute it is as 2y1 and both 2y2 minus 8 y1 y2, then what we are getting is, yeah, this is correct, right? 8 y1 y2 minus 8 y1 y2, and this is 0. So in the first case, yes, it is 0. And now second case, if x1 is equal to 2y1 or x2 is equal to minus 2y1, in that case, what I'm getting, x1, x2, I have this 2, x1, x2 minus 8 y1 y2. This is 2. x1 is now my 2y1. x2 is minus 2y2. Wait. This is minus 8 y1 y2. That in that case, it is what? This is 8 y1 y2 minus 8 y1 y2. And is this 0? No, right? But this needs to be 0. But if I substitute 2 points here, can we give a counter example where it is not happening? Is this really a subspace or not? This is a parabola, right? X square minus 4. I don't think this is a vector space, or is it? For example, let us take these two things. What are all the points which belong here? If I take 2 and 1 and one more, one more positive point, 2 and 1, and maybe let us take any point. I have what? X is equal to 2y. So if I take 4 and 2 and then add, then whether this, so let us check whether this 2 comma 1 plus 4 comma 2, this belong to that set, right? Because it is 2 square, 4 minus 4 1, and it is 16 minus 2, wait, 4 into 4, that is 0. But if I add those, it is 6 comma 3, and whether 6 square minus 4 into 3 square, whether it is 0 or not. So this is 36 minus 4 into 36, 4 into 9, that is 36. So it is 0. So what are we missing here? If I, this needs to be minus. So instead of 4, if I take minus 4, minus 4 comma 2, right? That's what I was taking. And in that case, this still belongs to the set because minus 4 square. And this is what? 4 minus 2 is 2. Minus 2. And this is 3. And now this minus 4 square minus 4 into 3 square. This now does not belong to the set, right? Because this is what? This is 4. This is 4 into 9. So this is non-zero. So this U dash is actually not a subspace. So you can check this. So this U dash, U is a subspace. U is a subspace of R2, but U dash is equal to xy in R2 such that x square minus 4y square is equal to 0 is not a subspace of R2. I hope this is clear. So there is an error in the question set. Understand this, U dash is not a subspace. We just have a counter example. We just chose 2 points from the set and it does not satisfy the given condition. I hope you understood this. That this point, this 2 comma 1, this belongs to my U dash, and this minus 4 comma 2 also belongs to U dash because it satisfies this condition. Okay, but their addition, this is this 2 comma 1 plus minus 4 comma 2. This point, this does not belong to my set. So this is not closed under U dash, is not closed under addition. So hence, therefore, U dash is not a subspace of R2. Is there any doubt here, like how we check that this set is not a subspace of R2?
Ma'am, could you explain it once again? I got disconnected in between.
Okay, sure. So what we were trying to check is, so first we proved that U is a subspace. Now we wanted to check whether this U dash is a subspace or not. And we tried to prove it. So the first condition got satisfied where both, from given condition. So see, we simplified the given sets. This is my set. Okay, x square minus 4y square is equal to 0. And I simplified it. X square minus 4y square is equal to 0 like this. A square minus b square. And I get either x is equal to 2y or x is equal to minus 2y. So 0 is very well there in this set. So now we moved ahead and checked for the second condition. That is, if x1, x1, y1 and x2, y2 are there in U dash, then whether their addition is there or not. So in order that to happen, we need to have this x1 plus x2 square minus 4y1 plus y2 square. We want this to be 0. So we started with the simplification from LHS of this equation. And we arrived at a conclusion that if this has to be 0, so we simplified this expression and we arrived here that 2x1, x2 minus 8y1, y2 must be 0. Then only this condition is satisfied. And so in order to check this, we have these 4 possibilities since x1, y1 and x2, y2 belong to my set U dash. And when we check for this first possibility that x is equal to 2y1 and x2 is equal to 2y2, in that case, it is satisfying the addition. We checked here. In that case, we are getting that it is 0. But when I have this possibility that x1 is equal to 2y1 and x2 is equal to minus 2y2, in that case, this kind of condition was arriving. That this x1, when I'm taking this 2x1, x2 minus 8y1, y2, which I wanted to be 0 for U dash to be subspace, this is actually getting minus 16y1, y2. So if this is the case, then this need not be 0 when y1, y2 both are non-zero. So we just wanted to check, we actually wanted to see the counter example. So we just chose these 2 points, 2, 1 and -4, 2 in U dash. We satisfy this condition that x1 is equal to 2y1 and x2 is equal to -2y2. And we got that this is non-zero. And thus we gave an explicit example to show that U dash is not a vector space. Is this okay? We were just checking the conditions and we arrived at a point where we saw that the condition is not satisfied, and we just try to obtain the explicit example to understand that given subset is indeed not a subspace of a given vector space R2, since it is not closed under
Okay,
addition.
ma'am. Thank you.
Yeah, okay. Okay, so now next question. So this U dash is not a subspace. So now let us see the third question. So for subspaces U and W of a vector space V over a field K, we have to show that first that the subset V minus U minus W is a subspace if and only if either U is equal to V or U is contained in W. These are the two questions which we, and second one is that if U union W is equal to U plus W, then either U is contained in W. Let me write this here. Then U is contained in W or W is contained in U. This is what is my question. Okay, so let us start with the first question that, let me just copy paste it from here. That I hope you understand what if and only if condition means. When we say that if a statement P is happening, then statement if, I mean, what this statement means is that both the implications should follow. That if the subset U minus V minus U minus W is a subspace, then either this should happen, and the other way around is also true, that whenever this happens, then this V minus U minus W is a subspace. So if I call this statement that the subset U minus V minus W, sorry, if this is P, and this statement that, let me just, if this is my P and this is my statement Q, then what I need to actually check is that this P implies Q and Q implies P. This is what if and only if means, that both the implications must follow. Okay, if and only if. So I'm just pointing this out because if and only if means P, or P if and only if Q means okay, this is what it means. Okay, and this has this symbol that P if and only if Q. So this is what equivalency. So if you see such kind of symbol, I hope you will understand what it means. Okay, so let us start with proving this. So first implication, that the subset, so they are saying that this subset, so this it's just subset, okay, this is just subset of V, and they are saying that this subset is a subspace. So this subset V minus U minus W is a subspace, is what we are given, and we have to prove this is given, and we have to now prove that either U is equal to V or U is contained in W. This is what we need to prove. So let us first understand what given statement is. So given statement is that V minus U minus W is a subspace. So if we try to understand this set, like what this actually means, so V minus U minus W is what? This is V minus U intersection W complement. This is what this set means, okay? So in general, A minus B means A intersection B complement. So it is collection of all those points in A which are not in B. So it is all those points in A which are not in B. So the point, and we want that both these conditions must satisfy that by those elements. So that's why intersection. Okay. But what this is just complement of this set, right? V is my superset. V is my universal set in this case because we are talking about subspaces of V. So this V minus U intersection W complement is just this complement, U intersection W complement whole complement, which is U complement union W. So in short, what is given is that this U complement union W is a subspace. This is my given condition. Now what I have to check is this either U is V or U is contained in W. This is what my given, this is what I need to check. So how to prove this? So what they are saying is whenever this U complement union W is a subspace, one of these two conditions must satisfy. That I either must get that U is V or U must be contained in W. So this we will try to prove by contradiction, that suppose none of these happens. Suppose U is not equal to V and U is not contained in W. So what does this imply? U is not equal to V. So V is my superset and U is not equal to the entire set V. So this is this kind of situation. This is my V and this is my U. Okay, so when I say that they are not equal, so there exists some point which is not in U but it is in V. Okay, so this implies that there exists some U in U, sorry, there exists some V in V such that this point V does not belong to U. This is what the first condition means. And second condition is like this, that my V is a whole set, and what they are saying is that W, this U, this is U, and this could be W. And they are saying this U is not completely contained in W. So what they are saying is that there exists some point in U which is not in W. Okay, so this point here is in U, but it is not in W. Okay, so what this means that there exists U in U such that U is not in W. So this is just, we are trying to understand that what it means. So we have these 2 points now, U and V and U. So if I take this point, this new point, what? Just, yeah. So no, so ultimately this U and V both belongs to my vector space V, right? So if so this point V minus U This belongs to my whole set V. That's not a problem because we are starting in vector space. U belongs to U means U belongs to V anyway because V is my superset. V is my universal set in this case. So this implies this V minus U either belongs to U or this V minus U belongs to U complement, right? If a point belongs to a set, I mean, this has to be there. I mean, given point, it must be either in U or it must either be in U complement. There is no other possibility for given point of set V. Okay, so if this V minus U belongs to U, and we also have that this U in U, and U is a subspace of V, then addition of these 2 points, V minus U plus U, this must also belongs to U, right? Any doubt here so far? So what is this? This is my V. This is V, and this implies that V belongs to U. But that's not true, right? This is contradiction. This is not true. As V does not belong to U to start with. V was not in U. But if V minus U belong to U, and I'm starting with U was my anyway inside U, and U is a subspace of V, then by that I should have that V belongs to U, but that's not true in our case. So this is not possible. And other possibility is this V minus U belongs to U complement, right? If a point from V is not in U, then it must be in U complement, right? So if this point is in U complement, then this also imply that in U complement, and also I have that V belongs to U complement from here, right? This V does not belong to U, that is V belongs to U complement, right? So I have this V minus U belongs to U complement and V belongs to U complement. So this also implies that this also belongs to this U complement union W, and V belongs to U complement union W, right? Is there any doubt here so far? If a point belongs to one set and I take union of that set with others, for example, if X belongs to A, and now I'm looking at the set A union B. So if X belongs to A, X also belongs to A union B. So this V minus U belongs to U complement and V belongs to U complement. Then now I'm looking at this bigger set, U complement union W and U complement union W. So both these points also belong to my set U complement union W. And now this is my vector space, right? This is vectors, this is subspace. This is given. This is my given condition. Okay, so we are actually making use of this fact that this is a subspace. So now, if that is the case, then this point V minus U or this V minus U must also belong to this set, right? Since U complement union W is a subspace. So these imply what? V belongs to U complement. Sorry, this implies U belongs to U complement union W. So if that is happening, then U either belongs to U complement or U belongs to W. But U we started from, so but U belongs to U here. U is a point of U. So this is not true. And also U is something that is not in W here. So this is also not true. So therefore, this is contradiction because we started from given condition that this point must be in U complement, and we arrived that U belongs to U complement or U belongs to W, which is not true. Okay, because since U belongs to U, since U does not belongs to W. So this is also not true, but V minus U is a point from my vector space V, element from my vector space V, but it is not in U and not in U complement. So that is absurd. So therefore our assumption or our supposition that U is equal to V, U not equal to V, and V not equal to W is not true, is false. Hence, we must have therefore, either U must be equal to V or U must be contained in W. Any doubts here how we arrived? So we wanted to prove whether one of these two conditions must satisfy. So what we assume that both of them does not hold. And we arrived at the conclusion that it's not possible that both of them are not holding. So that's why one of them must hold. And that's why either U must be equal to V or U must be contained inside W. Any doubts here? Okay, great. So now next implication, that we are now given that U is V or either U is V or U is contained in W. And we have to check now that this V minus U minus W is a subspace. And so now we have to check for both these two possibilities. This is actually giving a subspace. But before that, please understand that this given condition for the first implication, we actually use this. Okay, this was not something which is just there. We actually explicitly use this, that U complement union W is a subspace. Okay, otherwise we could not have arrived at this contradiction which we got here, this entire part here. So please try to understand what given condition is. If we had just left it at this point that this given set is a subspace, realizing how this set looks is difficult in first glance. So that's why we simplified this to understand that what exactly this subset is, and it is U complement union W in V. Okay, so this is in V. So, and it helped us here to understand that when we saw this and we wanted to arrive at some conclusion, we try to add them. If you just say this, that because V minus U belongs to U complement and V belongs to U complement, therefore this subtraction U must belongs to U complement, this does not make sense. This does not make sense because U complement is a not vector space. We wanted, the addition is close inside vector space, in subspace. And U complement is definitely not subspace because 0 does not belong here, because 0 belongs to U and we are looking at U complement. So 0 definitely does not belong to this U complement set. But we wanted 0 to be there. So we took union with W. W had 0, and now this new set U complement union W has 0. Has 0 and it might satisfy the properties of subspace. We do not care that because it is already given that U complement union W is a subspace. And then we made use of that condition that U complement union W is a subspace. Okay, so when you have to prove something, please understand what given condition means clearly, because somewhere while proving the statement, you will be using it. And if you do not understand what given condition is, then it will be difficult for you to proceed with the proof and so on. Okay, that's I just wanted to point that out, that we are explicitly using the given condition. And here also there are there are two conditions, that U is equal to V or U contained in W. So we will just check for both the cases. If U is equal to V, then this V minus U minus W is what? It is U complement union W, right? But what is U complement? U is V, so this is V complement union W. And V complement in V is just empty set. So this is empty set union W. So therefore, in this case, therefore, if U is equal to V, then V minus U minus W is just W. And this is anyway subspace. This is subspace. This is like, this is what we started with. This is, where is it? Yeah. So this is my original setup for the question, that U and W are uh, subspaces of V. So W is anyway subspace of V. So therefore this V minus U minus W is a subspace, because this is a subspace. So we proved the first, we checked it for U is equal to V condition. And the second was, if U is properly contained in W, then this V minus U minus W is what? U complement union W. This is what? U complement union W. Or before going to that, this, when we have this, wait, then this is what? U complement intersection W. But U is contained in W. So when I take U complement, this intersection W will be W itself. No. Will this be? What I wanted to say, that V minus U minus W, and when U is completely contained in W, this is actually empty set here. Can you see that? Because this is my V, this is my W. Wait, this is my W, and this is contained in V entirely. Then this is this set, right? And when I take complement of that, oh no, sorry. U is completely contained in V. So when I take U, yeah, U complement intersection W, this will be empty set. You can check this. This is what? U minus W, right? So this is all those point. This is all those point in V such that U belongs to U and U does not belong to W. X belongs to U. But if such point exists, if something belongs to U, then by default this implies that U belongs to W, since U contained in W. So therefore this set is empty because U is contained in W. So if some point is in U, then it has to be in W. But this is what? Oh, sorry. This was U intersection W complement. and not U complement intersection W. So it was U intersection W complement, but W complement is smaller than U complement. I hope you understood that this is now empty set. So therefore, when I take this V minus U minus W in this case, this is just V minus empty set, and that is V. And therefore, V is a subspace. V is anyway subspace of V itself. So therefore, this is also satisfying. So I hope you understood this. This is my W and this is my U. And I'm taking U intersection W complement. This is my U and W complement is this. So definitely the intersection is empty set. Is this clear? Is this statement clear? That U minus V is U intersection W complement. And in this case, since U is contained in W, this is empty set. So this is like this implies U belongs to W and U does not belong to W. Sorry, this X. So ultimately what I'm having is that X belongs to W and X does not belong to W. So that is not possible. These two conditions. And that is giving me empty set. So this V minus U minus W in this case becomes U minus empty set, V minus empty set, which is just V. And V is anyway subspace of V itself. And so both the conditions are satisfied. We proved this statement that in both the cases, V minus U minus W is a subspace. Therefore, yes, therefore, that's it. We are done with proof. Any doubts in this proof here? Have any doubts? Or anything which was not clear, or was it too fast? I hope this is clear. If there are any doubts, please let me know. Okay, I assume there are no doubts now. If you have, please write it in the chat box. Okay, I hope, yeah, someone said that it's clear. So let us move to second part of the question, what it asks. So it is if U union W is U plus W, then now this statement is if then. So we just have to prove the one implication. If the given condition is satisfied, then either U is contained in W or W is contained in U. Okay, this is what we have to prove. But before that, something more we need to understand here. First of all, this here. So if you look at the statement, it is just symbols that U in union W is U plus W. That's it. That's what is given to us. But what does this imply? What does this actually mean? So understand that this, when we write, this is sum of two vectors, vector subspaces. Okay, and this is what? This is all those U plus W such that U in U and W in W, and we have seen that this is a subspace. This is how it is defined, and this is the subspace of V. Okay, so when we start with the two subspaces U and W of V, when I take addition and it is defined like this, then it is a subspace of V. Okay, so when someone write this, that U union W is U plus W, what they actually mean is that this U union W is actually a subspace of given vector space. Okay, so when they are writing this, they actually mean something, that they are indirectly giving us information that this U union W is actually forming a subspace. So this statement here, this means that U union W is a subspace. And what kind of subspace it is? It is the smallest subspace. So U plus W is a smallest subspace which contains both U and W. And again, if you check the assignments, they are saying that why such smallest subspace first exists. So first of all, it forms a subspace. This set here, this forms a subspace. Okay, but why is it smallest among the subspaces which contain both U and W? So suppose we have this T, which is smallest containing both both V and U and W. Okay, so what this U plus W is, again, let me write here. This is what I need to check is to show that, or to understand that this T is actually U plus W. Okay, so what this U plus W is? It is U plus W such that U is in U and W is in subspace W. So when I take U here, and if I take this subset and 0, so that is U in U and 0 in W, this particular case, this just becomes U, and this is my set U, right? Just my subspace U, which is contained in this set, right? And similarly, I can take this 0 plus W, where 0, this particular in U, and so this is my W. And both of these sets are contained in this U plus W, right? So both this U is in U plus W and W also is in U plus W. So, and since I'm saying that T is the smallest, then T is smallest, that is, we are assuming. So this U plus W, so note that this U plus W must also be contained in this set T, because U is contained in T and W is contained in T. So for every element U here and W here, this U plus W must also be contained in this T. And this is what? This is this element belong to this kind of, this U plus W. And that gives me that this U plus W is actually contained in this T. But T was the smallest, and this is subspace containing both U and V, U and W. And this is my smallest subspace containing U and W. And this subspace is contained in my T. So what will that imply? That this will imply that T must be is equal to U plus W. Otherwise, this won't. If u plus w is not equal to t, then by this condition, this u plus w will properly be contained in t. So there will be some element in u plus w which is not in t, but that will contradict the fact that t is a subspace which is smallest. So here all the elements of this form are there, but they are definitely inside the set T, the subspace T. Okay, so the only possibility for that is T must be equal to u plus w. So therefore this u plus w is the smallest subspace containing both u and w. Is there any doubt here to understand that how this u plus w is a subspace? Subspace proving this is a subspace is not a problem. That u plus w is clearly a subspace. You can check this. And yeah, so now when they are writing that u union w is u plus w, then they are saying that this u union w is actually forming a subspace. Note that in general, this u union w is not a subspace. Okay, for example, the example of subspace which we saw, in the beginning of lecture today. If I take these two subspaces, this is suppose my x is equal to y. And if I take this another subspace, x is equal to minus y or y is equal to minus x, does not matter. Both these are subspaces. So if this is my w and this is my u, then both of these are subspaces. But their mere union, just taking these two lines is not a subspace, because if I take one point here, suppose this will be what? This is minus 1, 1. And if this is 1, 1, then addition of these 2 points is what? This is 0, 2, which is somewhere here. And it is not inside the union of these two subspaces, right? This 0, 2, 0, 2 does not belongs to this L minus 1, right? No, L 1 minus 1. This will be what? Minus 1, 1, 1. This is L 1, 1. And this will be this 1 minus 1, 1 minus 1. So this will be L union L 1 minus 1. Yeah. This 0, 2 is not inside union of these two subspaces. That's what I'm saying. So in general, this is not a subspace. But when they are writing, in general, this is not a subspace. But when we write that u union w is u plus w, then we mean that this u union w is a subspace. And it is, in fact, the smallest subspace containing both u and w. So the reason why I explained all this is that this might look like just some equation, but it actually means something. It means that this u union w, which in general not a subspace, is actually a subspace. So that's what given condition is. So what given condition is that u union w is a subspace. And it is not just some equation that u union w is equal to u plus w. So when I said that please understand the given statement, this is what I mean. In earlier case also, we try to understand what this structure actually mean when they are saying that this is a subspace. Now again, when they have given some given condition, what this actually means? This means that U union W is a subspace. If that happens, then either U must be inside W or W must be inside V. That's what U must be inside W or W must be inside U. That's what we need to prove. So let us start with that statement. I hope you understood what I'm trying to say here. Okay, so given that U union W plus is equal to U plus W, that is that U union W is a subspace of V. Okay, now we have to prove that either U is contained in W or W is contained in U. So again, we will again use the same method which we used in our earlier question. So suppose both these conditions are not satisfied. Okay, so this imply what? That there exists some U in U such that U is not in W and this there exists some W in W such that W is not in U. Right? So this U is in U, but U is not in W, and W is in W, but W is not in U. Okay. But both, since U is in U, this implies U definitely belongs to U union W. And since W is in W, this implies that W belongs to U union W. Right? And also, since this U union W is a subspace, this U minus W or U plus W, whatever point you want, U minus W or U plus W, this U minus W belongs to U union W. So now I have this U, W and U minus W, all three belongs to this subspace U union W. So this imply what? That this wait. U plus W. Let us take U plus W. So this implies this U plus W belongs to U, or this U plus W belongs to W, right? This is what it means. These two elements belongs to U union W. So this implies this addition also belongs to U union W because it is a subspace. So these imply that U plus W belongs to U. So this implies this U plus W minus U belongs to U because U belongs to U. Since U belongs to U, this imply, and then I get that W belongs to U. But this is not true. Since we started with W not in U. Okay, and similarly, since W belongs to W, I get that U plus W minus W belongs to W. So this is what? This implies U belongs to W, which is again contradiction or not true because this U we started with not in W. So both the cases. So when we say that U and W belongs to U union W, their addition must belong to U union W since U union W is given to be subspace. So since this element is in the union of two sets, this element must belong to one of these sets. That is either U or W. But we saw that if that element belongs to one of these subsets or subspaces, we arrive at a contradiction that W here, that in that case, if it belongs to U, then W belongs to U, which is not true. If U plus W belongs to W, then it is not true. So if it is not possible, then this U plus W belonging to U union W does not make sense. But that is there with us. So therefore, our assumption that both these conditions, that U is properly contained in W and, sorry, not, U does not contain W and W does not contain U. So our supposition, therefore, our supposition is wrong. That is, U and U contained in properly contained in W and is not true. Hence, U must be contained in W or W must be contained in U. Is there any doubt here? So that is the only, I mean, this is what we wanted to prove. We started with what is given and we arrived at that U is contained in W or W is contained in U. So any doubts here? It is the same method which we used in the previous question. And now let us see the next question. Yeah, this one. Let's see how much we can finish. So this next question, I think it is question 4, that the set of all functions. I hope there are no doubts. If there are any doubts in this previous question, please let me know. Okay. So that f from C to C with limit z goes to infinity, this f of z is 0, is a C subspace of the vector space CC. So when we say that CC, it is what it means, that it is function from C to C. That's it. Of all the p-valued functions on C. Okay. So we have to check that it is a subspace. And we know there are 3 conditions which we need to see. So function addition, I hope you how it is defined in CC. So f comma g, if I take from C to C, then f plus g is a function from C to C such that defined like f plus g of z is f of z plus g of z. And I mean, this is definition of addition. This is addition and scalar multiplication for C in C. So now, or omega, no, let us take A in complex. So we are now looking at it as C subspace. So the scalars are now coming from complex numbers. So, and if I take f from C to C, so when I write this imply f and g in C. That is, f is a function from C to C and g is a function from C to C. Okay, and if I take a complex number, and f is a function from its C valued function over C on C, then this alpha f is new function defined like this. This is multiplication in C. So this is just how addition and scalar multiplication defined in this vector space. Okay, this is a vector space which we are talking about. And this is how addition and scalar multiplication defined. Now this is new set. This is the set. This set, let us call this U. It is all those F in CC such that limit Z going to infinity, f of Z is 0. This is what my set is. And we have to check to prove that U is a subspace of CC. So first condition is to check whether zero function is there or not. So what is zero function from C to C is that 0 of Z is just 0. Okay, this is very bad notation, but yeah. So therefore, 0 yeah, let us call this zero function. We denote the zero function as 0 only. Let it be. Does not matter. This is function and it is function from C to C such that every element is mapped to 0. And this limit of this function 0 of Z as Z goes to infinity, it just limit Z tends to infinity. When this Z tends to infinity, I will explain what that means, is 0. Okay, and now to understand this, suppose now that this f and g are two functions here, and now I need to check whether this f plus g or not in CC. If I take these from you, I need to check whether the addition of those two these two elements belong to you or not. So first understand what this limit Z tends to infinity f of Z is equal to 0 means. Okay, so in R, when we take x goes to infinity, we often look at x going to positive infinity. It is easier to, when we are talking about R, it's easier to understand when we say something goes to infinity. It simply means we are looking at bigger and bigger numbers in bigger and bigger real numbers. So when Z we are taking as big as possible, f of Z, when I say limit f of Z as Z goes to infinity is 0, in R, it means as I take bigger and bigger element in R, uh, the value of f is getting as close to 0 as possible. That's what it means in R. But in C, what exactly it means? So this actually implies that for all epsilon, so it means that for all epsilon greater than 0, no, for not there, no. So for all epsilon greater than 0, there exists Z in C such that for all mod z greater than this mod z naught, this mod of f of z minus 0 is less than this epsilon. This is what limit means. Okay, so give me any positive epsilon as small as possible. There will be a stage where after that all the values of f are as close to 0 as possible. So that's what it means in C. So how to translate this in R? So if I wanted to look at R, so if I take limit a goes to infinity, f of a in R, okay? If I want to say this in R, what it means that for all epsilon positive, there exists some a in, there exists some b in R such that for all, a greater than equal to b, f of a minus 0 is less than this epsilon. This is what it means. So when I say limit approaches 0, as for any given epsilon, there will be some b. So for example, if I look at this e power minus x function, then it goes to 0, we know. So when I take some epsilon, there will be some b here, after which the values of that function all lie as close to 0 as that epsilon. That's what it means. And in complex, instead of this b, it is the modulus which exists. Okay, so C is whole plane, okay, and something goes to infinity is not very clearly to understand, because all these points are infinity if you look at. I mean, I hope it makes sense what I'm trying to say here. The in R, when we say that something goes to infinity, it either goes to plus infinity or minus infinity, and it is easy to understand. But in complex, when I say something goes to infinity, we do not have particular direction which it follows. Okay, because it is a plane like this. And when I say that something is going to infinity, all these points I'm looking at. And when I write something like this, that this mod z must be greater than equal to z naught, it means that I am saying that there is a circle. This, suppose this is my modulus z naught here. And any point, if I take outside this z naught, I mean this circle z naught here, I mean any point outside here, this f of z will be as close to 0 as your epsilon was. So this z naught actually depends on epsilon, and we can always find such epsilon, such z naught for a given function, because limit of this f is 0 as z goes to infinity. I hope you understood what it means, that function approaching 0 as z goes to infinity in complex numbers. I hope that was clear. Okay, if you have any doubt, please let me know. So we'll just apply this. We will just use this fact, and we are already assuming this f and g belongs to u. So since f belongs to u, this z1 instead of z naught, let me write again. So since, sorry, limit z goes to infinity, f of z is 0, this imply for for let epsilon be greater than 0. Okay, then for the then for wait, this limit z goes to infinity, f of z is 0. Uh, so this imply that f of yeah, there exists Z1 in C such that for all mod Z greater than equal to mod Z1, f of Z minus 0 is less than epsilon. And similarly, for this same epsilon, limit Z goes to 0, g of Z is 0. This implies that there exists Z2 in C such that for all mod Z greater than equal to, for all Z, it's not a for all Z in C with this, for all Z in C with this condition, for all Z in C with mod Z greater than equal to mod Z2, this mod of f of Z, sorry, g of Z is 0 is less than epsilon. So what I need to prove is that, so what to check that f plus g belongs to this, f plus g belongs to this u. So I wanted to check that limit z goes to infinity, this f plus g z is 0 or not. And this imply, so I wanted to check that for epsilon, this epsilon, if there exists some z naught in C such that whenever mod z, for all z in C with z greater than z naught, this f plus g of z minus 0 must be less than epsilon. Right? So instead of epsilon, if I take this z such that this is less than epsilon by 2 and epsilon by 2, and if we choose this z naught to be zi such that zi to be, we can't take addition actually. Okay. So we can take this z naught to be mod z1 plus mod z2. This still belongs to C, okay? Because this is some real number and this belongs to C. And if I take this, then for all z in C with z mod z greater than this z naught, this, understand that this plus this z minus 0. So if I omit this 0, this is f of z plus g of z. And now this is less than equal to mod f of z minus 0 plus mod, this plus minus 0. And now this is less than equal to epsilon by 2 and epsilon by 2, because this is anyway greater than equal to mod z1 and greater than equal to mod z2. So first and second both are satisfied. So this is equal to epsilon. So therefore this mod f plus g of z minus 0 is less than epsilon for all z in C with mod z greater than equal to this z naught which we chose. So therefore this, so this implies that limit z goes to infinity, f plus g of z is actually 0. Okay, and now the third condition, that suppose let alpha belongs to C and f belongs to, f belongs to this CC, and now we already know f belongs to, so not CC, f belongs to U, then this condition again satisfies, which I'm not writing again. But I now want something that, okay, there's no question, right? Uh, yeah, we are little over time, but let us finish this. So what we want is, we want to check that this alpha f belongs to U or not. So what we want that for all epsilon positive, there exists some z naught in C such that this, whenever for all z in C with mod z greater than equal to mod z naught, this alpha f z minus 0 must be less than epsilon. Okay, so if alpha is 0, the functions become 0 and we are not taking that case. So if alpha is 0, nothing to prove. Let me just write. If alpha is 0, nothing to prove. So suppose alpha non-zero. Okay, so I want this, right? So what we can do here is that since f belongs to my set U, this is happening. But instead of this, now what does this imply? I want this f of z to be less than epsilon by alpha, right? So f, this I want. So instead of this, if I take this less than, so let epsilon minus alpha, I choose this, and for this epsilon dash, which is epsilon by alpha, this happens. This will happen. This is my new epsilon, but for this also I will get some z1 such that this happens. And then I choose this z naught is equal to z1. And then what I will get, that then for this, for let z naught is equal to z1, then for epsilon positive, and for all z in C with mod z greater than this mod z naught, this alpha f of z minus 0 will be just this mod alpha f of z, or we can take alpha here, mod alpha here, because this is complex number, and then this does not make sense. For these inequalities, everything must be real, okay? You can't talk about what order in complex. So these are all real numbers. So this, and since, so this is definitely less than epsilon, because this is there, then mod alpha mod f of z is less than epsilon. This implies mod alpha f of z less than epsilon whenever z is greater than equal to this z naught, which is z1. Okay, and so therefore this limit z goes to infinity, alpha f of z is 0. Okay, any doubts here? Okay, great. So this is some analysis which we did, but yeah, you need to, if you want good marks in assignment, you need to write all these details. But I hope you understood that we checked all these three conditions. 0 is there, addition of two functions is there, and scalar multiplication is also there. And I hope you all understood what it means when we say that, I mean, this structure. What exactly this means in complex number. I hope you understood that as well. That what it means, that limit z goes to infinity f of z is equal to 0 in complex numbers. Okay. So I mean we are anyway over time. So any doubts so far what we did? If not, then we can end the session. If you have any doubts, please ask, or if you still have any doubts from what we did here, I mean, you can ask, you can access the lecture notes and video in which book to refer. I mean, there are no references given. Okay. I mean, there is what we say. Is it allowed? Okay, to exchange phone. I mean, you can exchange your phone numbers here. That's not a problem. I mean, I won't be sharing my numbers, but among yourselves, if you want to share numbers and form a group, you can do that. And if you want to do that, you can. I mean, we anyway have discussion forum, which is anyway group which is accessible, which is kind of a group which is accessible to everyone, which is part of the course. So if you want to discuss something over emails, discussion forum is already there, and even we will be there. I mean, both of us who are conducting the tutorials and the team for the course which deals with your assignment, grading, and other stuff. So if you want to discuss, discussion forum is already there, and if you want to exchange your number, you are free to do that in the meeting. And those who want to contact you can do that. And okay. So you can follow basic books which are there. I mean, in the course plan, it will be mentioned which books to follow. If it's not there, I mean, all the notes are already shared with you. And if you need a book, you can raise that question in the discussion forum, which books to follow. And we will write it there. If you ask me which book to follow, uh, where you can join the discussion forum, you don't need to do anything in the discussion forum. So when in the portal, there is Q&A section. And once you click on that, you are directly, you will be like forwarded to the link of discussion forum. Yeah, it is Google group. Yes, and you can raise your questions there and all your queries about syllabus, about grading, about the final exam and exam recitation and everything. Even NPTEL team also monitors that discussion forum. So if you have any doubts related to registration and exam registration, you can raise those as well in that discussion forum. So yeah, discussion forum is the place where uh, most of your queries will be solved. Yeah. Any doubts related to the question? I mean, related to this tutorial session, which we did. Okay, I hope there are no doubts. Okay, if there are no doubts, then let us end the meeting, and we'll meet next week, same time. Thanks.